Let's do 11.6. We're going to go back and revisit our exponential and logarithmic functions. But now focusing a lot more on the graph. Exponential and logarithmic functions. Today we'll just focus on the exponential. And then tomorrow we'll have a little extra time. We'll look at logarithms as well. So let's start with the exponential and how we use modeling for the exponentials. So here we're going to define our model that we will look at. And our exponential model will look like something like this. F of x is going to be some coefficient. We'll use the same coefficient, a. Some base little a raised to the bx power plus that same idea of an offset. Now, a is kind of like an amplitude, but it's not quite an amplitude. But we want to see what happens to the graph of this as a capital A, capital B, and little a and b change. So what happens as we change these parameters to the graphs of our exponential function? Well, one of the first things we're going to understand is that a over here, little a, has to be positive. So it can't be 0 and it can't be negative. I can't have a negative as my base. So that's a restriction that we have part of our definition. So a has to fall into that category. And then we see some interesting aspects of a. Now, b can be anything. So there's a lot of different interplays here between this a and this b. For example, let me show you one sort of problem. Let's just take b to be 0 and a to be 1, and let's explore the interplay between lowercase a and lowercase b. So say, for example, I have the following. So this is true for everything. Let's say I have 1/2, and I just let b equal to 1. So I have 1/2 to the x power. Then I ask the question, what happens? Let's let x go to infinity. And what does that graph look like? Well, if I were to plot this on my computer or calculator, it would look something like this. So when x is 0, 1/2 to the 0, it always goes to 1. But what happens here is x gets larger, I'm multiplying by factors of 1/2. You know, if x was 2, that's 1/2 squared, which is 1/4. If x was 3, that's 1/2 cubed, which is an 8. So what happens is kind of counterintuitive. It goes like this. So we call this a decreasing exponential. Now, what if I take something like this? F of x is equal to 2. Now I take a to be greater than 1, and I put to the minus x. Oh, let's take a look at the graph of that and see what happens. So again, I still go through that same location. When x is 0, I still go through 1 over here. But now as x goes negative, it actually decreases. So this is also a decreasing exponential. Now you might have noticed over here an interesting little property. As x goes to infinity, this is what happens. These are actually related to each other by the properties of exponents. Remember, 1/2 is equivalent to 2 to the minus 1. So 1/2 raised to the x power is equivalent to 2 to the minus 1 raised to the x power, which is 2 to the negative x. So you can see there's kind of an interplay between the a and the b. In the end, if b is negative, and I'll put it over here. So let's kind of put the relationship. So if 0 is less than a is less than 1. So little a is a fraction. And B, this coefficient here, is positive. Then you're always going to have, your graph is always going to be what we call a decreasing exponential function. It's always going to be in this form over here. Now this is one, unless of course we have a B that might shift it, or an A value here that could shift it as well. A and B will shift that location, but now I'm just doing a 1 in front of everything, because there's all these little complexities that can happen. So what happens here, then we know as x goes to infinity, the f of x that I've drawn over here goes to 0. That's the end behavior. And the other side of it, so as, let's do it on this side, as x goes to minus infinity, then f of x goes to plus infinity in this graph. Now, where might it change? If this a over here, capital A, happened to be negative, then it would flip the other way. Then it would look downward. So this is a is positive. So all these little things, we're looking at the interplay of these parameters on the graph of our function, and they all have a role to play. Now, what about if I have this? So if, say, a is greater than 1, and b is also now positive, let b be positive. This is what happens to my graph. I'm still going to go through and get my same sort of thing, passes through 0, but now it looks something like this. So here, as x goes to infinity, then my f of x will also go to infinity. Unless, of course, I put a positive a over here, putting 1 over here make it a lot easier. And as x now goes to minus infinity, my f of x goes to 0. Well, that brings up an interesting point, especially for these two cases right here. In both of these cases, as x goes to either plus or minus infinity, I am going to have constant, a fixed value. That's the definition of a horizontal asymptote. So that's what comes out of our exponential function, the idea of a horizontal asymptote. Any exponential function will have one. It doesn't go in both directions, it only goes in one direction. So all exponential functions have a horizontal, anything we define for a rational function, asymptote. They will always have it. And it either occurs, it's either as x goes plus infinity, or it occurs as x goes to minus infinity. You have to, it depends upon which graph. This one occurs for x going to plus infinity, and the other one occurs for x going to minus infinity. And you can see it on the graph. Now, what is that horizontal asymptote of my function? So let's go back to this. So f of x is equal to, in this case, a, and let's take my a to the bx plus b. Well, the horizontal asymptote is always going to be my offset. So the horizontal asymptote, we call it HA, for all exponential functions of this side is y is equal to b. That'll always be the case. No matter what this is, you know, A or B are, what the, you know, if that's positive and negative, if that's less than 1 in magnitude, or I mean between 0 and 1 or greater than 1. Horizontal asymptotes are always that. Now, if I don't have anything over here, like I've drawn over here, this in each of these cases, my b value here was 0. So that's why my horizontal asymptote for each of them was y equal to 0. So that's what an exponential function has. It has a horizontal asymptote. Now we know the domain for any exponential functions are all real numbers. The range depends upon this now. So let's take a look at a few of these and get a sense for what I just put up here. So I'm going to look at a few examples and you get a sense for what they look like. So say I have one example, f of x is equal to, let's do 2 e to the x plus 1. Let's take a look at another one. F of x is equal to a minus e to the minus x plus 2. And let's take a look at a third. Let's do f of x is equal to 3 times 2 to the x minus 3. So let's take a look at these three functions and look at their graphs using Desmos so we can get a sense for what we're looking at. Okay, let me clear this out. Clear, clear, clear. And let's put each of those out. So y equal to 2 times e to the x plus 1. And then I get y equal to minus e at minus x plus 2. And then over here, let's take a look at y equal to 3 times 2 to the x minus 3. So look at them each individually. And I got to zoom out a little bit over here. Let's just show up these and we'll examine the first one. So I'll zoom out a little bit over here. So if I look at this one, and if I look at the line x equal to 1, let's just plot that line as well too. Or excuse me, y equal to 1. Keep me awake. Whoa, y equal to 1. We can see that the first graph has that horizontal asymptote at y is equal to 1. When x now goes to minus infinity, this becomes indistinguishable from that graph. So there it is, y equal to 1. Now as x goes to plus infinity, you can see this goes off to positive infinity. So this horizontal asymptote exists only as x is going towards negative infinity. Okay, let's take a look at the next one over here. Now this one, move it down over here, you can see the coefficient, the number at the end, that b value, as I said, if I now look at, say, y equal to 2, that also becomes the horizontal asymptote. So what happens over here? Well, as x gets really large in the positive sense, e to the minus infinity goes to 0. So this just goes to 0. This term goes to 0 over here and just gives me 2. Same thing over here. As x gets very large in the negative sense, I get e to the minus. That means I'm dividing by powers of e. So this term goes to 0 and it just leaves off the offset value over here. Same thing happens over here. If I take a look at this one, and let's take a look at, let me just take a look at 3, make sure I got it correct there. There we go. There we go, that's better. That actually gave me 32 to the x. I didn't think it was going to do that, but it put a 32 in there, and that's not what I wanted. So here's a graph of this function. Now I'm looking at the value y equal to negative 3, and yes, that too is indeed a horizontal asymptote, but as x goes towards negative infinity. So if I put a negative in for x over here, that's 2 to a negative power. That's dividing by powers of 2, so this gets smaller and smaller, and that goes to negative 3. So for all these cases, we can easily, very easily pick out the horizontal asymptote of any exponential function. So my horizontal asymptote here, I can ignore the exponential function, and that is y is equal to 1. And that occurs, since let's say this value e is greater than 1, and that's a positive exponent, that occurs as x goes to negative infinity. This also has a horizontal asymptote of y equal to positive 2. E is greater than 1, it's 2.71828. That's a negative exponent, so that occurs as x goes to positive infinity. I'm looking for the value of x that'll make each of these exponential portions go to 0. That will make that go to 0. Going to positive infinity will make that go to 0. Just leave that. In this case over here, I have a horizontal asymptote at y equal to negative 3. And it occurs as x, since this is greater than 1, and that's a positive exponent, that occurs as x goes to negative infinity, which will cause this to go to 0. Now, if I had something slightly different, say this, f of x is equal to 1/3 to the x minus 1, well, I'm correct in stating that the horizontal asymptote is y is equal to negative 1. But what does x have to go to, plus or minus infinity? Well, since this is between 0 and 1, x goes to plus infinity for that to work out. And another way of seeing that is I can rewrite 1/3 as 3 to the minus 1 and raise that to the x power. And that'll give me 3 to the negative x, and it'll kind of look a lot like this one over here. Not the same, but similar to it. Okay, so that's the features that we like to talk about for our exponential functions. They will have a horizontal asymptote. All of them, no matter what the base is, every exponential function. Now, usually people, if you don't have anything over here, then it's 0, and they usually forget this. And that's where it usually is a problem. Okay, then that raises the question, what about the range? We know the domain is all real numbers, but what about the range of these? Let me leave those functions up over here, and let's talk about the range. And maybe one more as well. What is the range of an exponential function? So that's the y values that will come out. So I'm looking at the range. And I'll do, in fact, I'll just do one more over here. Let's do one over here. F of x is equal to 2 to the x. So the range over here. Well, if I look at this one, I'm going to get rid of this. I'm no longer letting that go to 0. And let's take a look at the pictures of each of those functions. I'll draw them over here just so you can kind of see this. Well, over here, I can see I'm going to go to plus infinity. As x goes to infinity, that goes to plus infinity. In fact, it's actually a little bit higher. It goes up here. Excuse me. I got to be careful. Goes to 1. Don't want to mislead you. In my head calculator, got to take everything into account. But the problem over here is the range is the output, the y values. So I can see y is going to be greater than negative 1. Will y ever equal negative 1? Will f of x ever equal negative 1? Well, the answer is no. It can get close to it. As x goes to infinity, I get closer to negative 1, but it will never equal negative 1. So the range for this, the set of all elements y is obviously a real number, but y has to be strictly greater than negative 1. I'm never going to get an output of negative 1 and never get anything beneath it. Same thing will happen over here. If you take a look at this one, this is a little more subtle if we look at the graph. You should always go to the graph for these to kind of help you out. So we have our, let's put in our horizontal asymptote. And if I'm graphing this, well, this looks something like this. And so that should be 2, and it comes down to something like this. What is the range of this? Well, now, since this negative's out here, this will go down to negative infinity. So my range for one, set of all elements y is a real number. But what condition? Well, y has to be less than 2. It's never going to hit 2. There's no value that I can put in for x that'll give me f of x equal to 2. It'll get very close to it, but it will never be equal to it. So it's always less than 2. Okay, so for these, for 3, 4, and 5, tell me what the range is. I'll have you do that on your own. Tell me what the range is for 3, 4, and 5. What are the range of those functions? Forget about that red there. Never equal to, but it's always greater than -3, greater than -1, greater than 0. Because this is like having a plus 0 over here. So that's the other thing that's important for these exponential functions, understanding their ranges. Any questions on that? And you can just plug them into your calculators. I like to use Desmos. It's quicker than the regular calculator, so kind of easier to use in that regard. Okay, so what's new about the exponential functions that we've added? Well, what we've added is a new horizontal asymptote. It has that. And we can see over here, this one is decreasing as I go this way, and this is increasing. It keeps increasing, but it's slowly increasing. So I have an increasing exponential function. Some of these, if I have a negative exponent like this one over here, that's a decreasing. Number 4 would be a decreasing exponential function as x goes to infinity. So that's the other thing we want to look at, and it'll ask you about if it's a decreasing or increasing exponential function. So let me put the important features. So the new important features, and we'll end with this, that are involved with exponential function. First thing we have is they have horizontal asymptote, so finding that horizontal asymptote. The second thing is new focus on the range of that. And then the third thing that's also important, is it an increasing or a decreasing exponential or function as x goes to plus infinity. That's what we're really concerned, going to plus infinity. As we go out, does it increase or does it decrease? Does it go up or does it go down? Now, it still can be decreasing and go to a fixed value. It just slows the decrease as we go along. Okay, so that's the thing I'm going to go to the textbook because there's a lot of different models. Now, all of these models we've essentially looked at prior, but we kind of did them again just to show you how you can use these. So I'm not going to go into a lot of detail on these since we've already touched on many of these prior to this. So I'll show it, and you can take a look at some of the examples. They're not that complicated. It's not anything we haven't seen before. So for the exponential functions, there's what we call a compound interest growth model. So the amount A of t over time is based upon some initial principal amount, A0, times 1 plus the interest rate written as a decimal. N is the number of compoundings in a time period, and t is the time that's defined. Usually it's N is compoundings per year, and t is the time in years, but it doesn't have to be that way. And as long as you know that, you can work problems for how your bank account may grow or your investments may grow if you have an estimate of that. So that's this is the x, the base over here, 1 plus r over n. That's the kind of the base, and the exponent is the nt. Compound interest grows. We've also looked at, and this shows you that was discrete compounded, compounded over a period. Then you go to continuously compounded growth, and we looked at that earlier. And the 1 plus r over n becomes essentially e with some minor modifications. The continuous compounded growth, you have some initial amount, e to the rt. So we've seen all those back in chapter 3 as it states over here. But we put them in here again just to give you practice. And radioactive decay, the other one was an increasing exponential. Here k, the positive constant. So in this case, we deal with a decreasing exponential, and you have radioactive decay. So we just have some very basic problems there again. Okay, our now focus is going to be on the logarithms. So we know that logarithms and exponential functions are inverse functions of each other. So for example, let's take a simple f of x equal to e to the x. And here's a graph of that function. Looks something like that. And we also note here that in this case, the line y equal to 0 was my horizontal asymptote for that function. Because as I go to negative infinity, it gets closer to 0 for the end behavior. Here it goes to plus infinity. Now we know that the property of an inverse function is all you need to do is essentially take the line y equal to x, and you flip your graph of your function about that line. So this now becomes a function that looks like this. And they're mirror images about the line y equal to x. Now, what happened to this horizontal asymptote for my exponential function? Well, that flipped up, and what does it become? It now becomes a vertical asymptote for my other function over here. So this is over here, you take your x equal to 0, and this satisfies the idea of a vertical asymptote. And it makes sense because they are, if you will, inverse functions of each other. So that's what the unique characteristics of logarithmic functions is, that they have asymptotes where the exponentials have horizontal. And you can test those by, as x goes to 0 over here from the right. So if I'm looking at this, as x goes to 0 from the right-hand side, This is my x-axis here, and I'm going to 0, and that plus means I'm going to it from the right. So I say as x goes to 0 from the right-hand side, in this case, f of x equal to the natural log of x, then my f of x gets closer and closer to negative infinity. And that's the definition of either plus or minus infinity. That's the definition of a vertical asymptote. So that's what's unique about the logarithmic function, is that in this case, they have vertical asymptotes, whereas the exponentials have horizontal. Now, the other thing that's true is we know that the domain for the exponential, remember the domain here, x could be any real number, and the range has some limitations on it, depending on it. In this case, for this specific example, is that the y has to be strictly greater than 0. But if I put a negative in front of that, it would flip it down. If I move this up and down by putting an offset, it might change. But there was limitations on the range. Now, if I look at over here, my logarithmic function, well, the range over here is all real numbers. And it should, because it's swapping the x and the y. But the domain has the limitation placed on it. And over here, the domain for this one is x has to be strictly positive. It's strictly greater than 0. Can't be 0 because it's hit my vertical asymptote would be undefined, and there are no negative values. But that makes sense because when we take the inverse of a function, we're swapping the domain and range of it, for the most part. So that's what you see. There's a big, unique factor of logarithmic functions, just like the rational functions can have a vertical asymptote. A logarithmic function will always have a vertical asymptote. And, sometimes they have actually more than one, depending upon the argument of the function. You might have actually more than one if you're looking at things. But for the most part, it's just that one case over here. Okay. Any questions on that? So what you'll be asked to do over here is to simply find the vertical asymptote. And how do we do it? Let's take a look at some problems over here. Here's some examples. Say I have f of x is equal to, say, the log in the base 2 of 3 minus x. Well, the vertical asymptote is always going to occur when the argument of the log function is equal to 0. Very simply. So what I do is I set 3 minus x equal to 0, and I get x is equal to 3. Well, the x over get x equal to 3. So how would the graph of that look like? Okay, so I come over here, and I come over, and I put my x value of 1, 2, 3. This is going to be and you can plug this into your calculators or into Desmos. That's going to be my vertical asymptote. Notice there's a negative in front of the x. So x can't be greater than 3, otherwise it would be undefined. I have to log of a negative value. So what happens? This goes in the opposite direction. So the graph of this function will go more like this. So if I take x is 0, log of 3, so when does that go 0? So that is equal to 2, so it looks like 2. This goes something like this. That's what the graph looks like. And there's my vertical asymptote. Now, if this was a positive, it would be flipping the other way. If that's x plus 3, it would go in that direction. But actually over here. Because then that negative 3 would be the one. So if I had x plus 3, it would flip it over. Let me just show you that. If I mentioned it. And if you're not sure exactly how these goes, you could just plug them right into your calculator or plug them right into Desmos, and you have your answer. And like on the test, I'm going to try and have Desmos hooked up. I'll know better shortly. But like I just said, say I took the opposite. Say I take the log and the base 2 of 3 plus x or x plus 3. Now my vertical asymptote occurs when x equals to -3. So this would look very similar over here. And now I go 1, 2, -3. That's my vertical asymptote. And what is the graph of the function like? Well, in this case, it's going to look like this. Because I can have x going positive. I just can't have it to the left of -3 because that would give me a negative argument in the logarithm, and it's undefined. It doesn't make any sense there. So it's easy to find the vertical asymptotes of the logarithmic function just by setting its argument equal to 0. Now, you could have more than one. Here's an example when I might have more than one. So say, for example, I had problem 3, f of x is equal to the natural log of x squared minus 1. Again, go through the process of setting that equal to 0. And I could factor this. Gives me two values, 1 and -1. So when I look at the graph of this, I now have two vertical asymptotes. I come over here at -1 and over here at +1. Now, this tells me over here x has to be greater than 1 for this to work out. Otherwise, if it was, say, 0, I get the negative. No, nothing works over here. So it looked like this. So there it is, my vertical asymptote. Notice x can't be between, -1 and +1. If it is, that's a negative argument. So there is no function drawn over here. And on this side, it looks like that. So I have my vertical asymptote here at -1 and another one here at +1. So it depends. By just setting the argument equal to 0, you can find out, you want to find all those excluded values. That's the window, kind of the wall that separates the positive from the negative values for the argument. I can't have negative values and I can't have 0. That's the wall that becomes 0. And that's all it is. Okay, so that's all you have to do, as well as we have a similar model for the Richter scale model for logarithmic functions. So kind of go over that as well. So that's essentially all the